Thank you. Thank you very much, and thanks for coming out, everyone. So the previous speakers have talked a lot about model improvements, improving components, improving parameterizations of this or that. We're an operational streamflow forecasting agency trying to take advantage. Sweet, thank you. We're an operational streamflow forecasting office trying to take advantage of these improvements that are being developed in the research communities. And it's not such an easy thing to do to get across this gap. But we have a project, a multi-year project going with NASA and a group at JPL that involves bringing some of the remote sensing data in that their group produces and using it in our operational streamflow forecasting processes. And my co-authors and I are listed on this first slide, but there's a group of 10 or 15 people that are behind this, and I have their acknowledgements in different places in the presentation. So I don't want to say, hey, these 4 people did all the work. It's this great team of people that are actually working together. So what is CBRFC? I work for the Colorado Basin River Forecast Center, which is part of the National Weather Service. Excuse me. We have a staff of about 15 people. 10 are hydrologists. We do have 1 vacancy open right now on USA Jobs. Closes on December 29th, a little plug there. We have a management position that's not yet open. And like I mentioned, we do operational streamflow forecasts across the Colorado River Basin and the Eastern Great Basin, which covers a large part of Utah. In the CBRFC area of responsibility, the hydrology is highly variable. Most people and many of our stakeholders are focused on the snow-dominated basins in the northern part. But flash flood hydrology is important in Arizona, but I'm not going to talk about that today, obviously. We have 500 streamflow forecast points that we issue daily forecasts for, and those forecast points, those basins are divided into elevation bands or elevation zones. So we have actually over 1,000 modeling units. Some of our stakeholders include other parts of the Weather Service, Bureau of Reclamation, water conservation districts, basically people who are managing reservoirs and water in the West, which is a huge group, a wide variety of people. So the point of this partnership was to take some of the advances that have been developed in terms of data sets, in terms of modeling, and try to get those into an operational forecasting office to try to improve our forecasts for our stakeholders who are depending on those operational forecasts. And we also wanted to build some understanding and communication between the research groups and the operational groups. There's a pretty wide gap in terms of understanding in remote sensing science, in snowmelt modeling, and it's been really useful for us at CBRFC as operational hydrologists to get some insights on some of the details of the advances that are being developed. The operational snow model that we use is Snow 17. Yes, it's old. It was written before I was born. We're still using it. But it requires minimal inputs, minimal computational power. There's decades of Weather Service experience. People are used to using it. They know how it behaves in certain situations. It's calibrated to streamflow using a 30-year period, and it's a temperature index snow model. It doesn't have a full representation of the energy balance. And it does pretty well a lot of the time. People say, well, we need a more advanced model for this or that. And in certain situations, yes, absolutely. But in near normal conditions, Snow 17 does pretty well. So the remote sensing data sets that we're using that are coming out of the NASA JPL group, we have primarily 2 types of data sets that we're looking at: a fractional snow cover, gridded product, and a dust radiative forcing product, which is an indication of changes in albedo at the snowpack surface. And we're using that primarily to judge the potential for accelerated melt rates so that our forecasters can be aware and make corrections to the simulations if they need to do so. So just a brief overview of the project timeline-wise. It started in 2012. Prior to that, our office was deriving snow information from point sources like SNOTEL. SNOTEL is hugely important to us. When I give these talks, I'm not saying, oh, we want to replace SNOTEL and we don't want to use the points anymore. We're going to go with fully gridded remote sensing products, fully gridded products, just period. The SNOTEL network is immensely important, and we're not advocating getting rid of that, but we're looking at combining data from the point networks with the remote sensing data to get a more complete picture of the snowpack. So in 2013, we actually started using the snow-covered area data, and we would make minor adjustments to the model, mostly towards the end of melt season, to add snow back in or take it out when the satellite product indicated that the snow was gone or it was still left when our Streamflow simulations departed from the observed. And in the past melt season, we started using the dust data a little more prolifically. And next year, we're looking at refining some of the methods that we've used in the past couple years to something that's more robust and narrows the range of adjustments that the forecaster would make. So saving them some time, like, hey, here's a more informed range of adjustments you might make, instead of, in some cases, guessing willy-nilly, trying to get the right answer in the Streamflow simulation for a reason that might not be supported by data. So this is just an example of snow cover product. We have two versions of the ModScag, which is a MODIS-derived snow cover product. We have a viewable snow cover product, which is more accurate in a remote sensing sense. It's what the sensor sees, so to speak. In the panel on the right, it's a canopy adjusted product, which if in the remote sensing retrieval, snow is detected and a green vegetation member is detected in the ModScag model, the snow cover value is adjusted upward. So it makes more sense to use this hydrologically. And then coming up on the horizon for next year is Veras-based snow-covered area. If MODIS dies, Veras is the follow-on instrument for that. MODIS has been doing great. We hope that doesn't happen anytime soon, but just in case, we're making preparations so that we have that follow-on data and we're familiar with it before MODIS does kick the bucket. So one use of the snow-covered area that we've developed in the last year or so is to look at a climatology, a snow-cover climatology that's specific to us at CBRFC. I mentioned that we divide basins into elevation bands or elevation zones, and we've computed the snow-covered area over those elevation bands, and all of our calibration at CBRFC is done manually by a forecaster. There's not a numerical optimization scheme that we're using. So if we can save the forecaster some time by having an analysis of where the snow is, at what elevation bands does it typically exist, that gives us the ability to fine-tune parameters a little more quickly and hopefully more accurately. So I want to give an example of a real-time forecasting challenge encountered by one of our hydrologists who was on duty, who used the MOD-DRFS dust data to make an educated decision of how to adjust the models, the streamflow simulated by the model. So there's a combination, let me go back, there's a combination of information that goes into decisions. When CBRFC puts out a forecast, a human reviews that forecast before it's issued to stakeholders and users. It's not just strictly a model-driven forecast. There are manual adjustments made to it. So we're using some information from a historical analysis that came out of Annie Bryant, now Burgess PhD work, field observations from Chris Landry's group. Mike, who just preceded me, mentioned a couple papers by Chris. He's got a program that monitors dust layers in the snowpack in Colorado that we use and monitor. We have the remote sensing products from JPL, and then we have forecaster experience and knowledge of future weather possibilities. Because we are using a temperature index snow model, we have to know something about the air temperatures. And a lot of our hydrologists in our office are trained also as meteorologists. So the historical analysis, this is my favorite graphic that came out of Annie's work. Basically, it shows in southwestern Colorado, which is one of the areas in the United States that's most prone to dust deposition in the snowpack, that the dustier the snowpack is, or at the surface, the dustier the conditions are, the earlier the observed melt actually happens than what we forecast. So this is a piece of information that our forecasters can keep in mind when they're anticipating those potential melt rates. I mentioned the field observations. This is a photo from Chris Landry, shows a couple dust layers and a snowpack, and this is from early April. And he sends out alerts via email on a mailing list that says, hey, these are here in the snowpack, be aware of them. And they're coming depending on how quickly this part of the snowpack melts off above those dust layers. There's remote sensing data. This is a time series of images from southwestern Colorado showing the dust radiative forcing product from JPL. And April 8th was, the dust layers were still pretty covered, but you can see that the images get redder as time goes on. And there was a storm on April 13th. There were the grayest clouds. And they were coming in on the 12th. So there was a storm on April 13th, and then this fresh snow covered up the dust layers again. The dust layers were getting exposed at the surface of the snowpack between April 8th and April 11th. And again, I've mentioned that our forecasters are taking this combination of information to make an educated decision when they're forecasting. So these are field photos from Chris Landry again from the upper Animas River watershed in southwestern Colorado, where the green star is. The city of Durango, Colorado is the yellow star at the outlet of the basin. And it's comforting. Our forecasters in our office, they're cautious creatures. They don't trust things easily. But it's when we have a remote sensing information, we have field observations, we have some forecaster knowledge, our forecasters then feel more confident in making some changes to the model simulation. So weather forecast, air temperature doesn't really melt snow, but we have an air temperature index snow model. So our forecasters were anticipating over a multi-day period above average air temperatures in southwestern Colorado. And this is a plot of departure from mean for several days in mid-April. And there was a 4-day stretch where temperatures were nearly 8 degrees C above normal, closer in the range of 4 to 6, but by quite a bit. So our forecaster takes all of this information, the field observations, the remote sensing, their experience, their knowledge, and makes an adjustment to the model simulation, which is shown in blue here. The red is recent observations. And so what they can do is, quote, crank up the melt. We have a couple of different modifications we can make in our forecasting system that accelerate the snow melt manually. And then the idea is that if your recent observations match your simulation, your forecasts going forward are going to be better. So how did this work out in this one case? So this is mid-April 2014, what I've been describing. The dotted lines down here are prior to that manual adjustment by the forecaster. The dashed lines that are just above are after, forecasts issued after that adjustment was made. And are they perfect? Is there still a lot of, no. Is there still a lot of improvement? Yeah. But it's the movement has been in the right direction. And so there's, I just did a very basic error computations, and there's a pretty dramatic decrease in error after that manual adjustment was made. So that's exciting to us as operational forecasters. The research community is doing so many amazing advanced things, but the operational forecasters are kind of jacks and jills of all trades. We do all kinds of things, not just snow hydrology and snow melt forecasting. So, our full-time jobs aren't devoted towards researching that. And one of the benefits of this partnership has been to gain some knowledge about the details of snow hydrology and snow melt modeling. So where do we go from here? Our current system, as it is, allows manual adjustments to the model simulations. So we'll keep doing that. There are some plans, I think, to improve the MODIS data sets. MODIS can't see through clouds. If we can get some gap filled or estimates of snowpack information on the cloudy days, that would be helpful to us. Our stakeholders, the CBRFC stakeholders, are starting to ask for maps of the remote sensing data. Hey, I want to see in my area where, what are you guys looking at? Where is the snow for my area? JPL is working on the Airborne Snow Observatory with very fine resolution SWE maps that we may be able to use. And then it's becoming increasingly obvious that CBRFC doesn't have an energy balance snow model, and that's something we need. So part of the project part of the JPL collaboration that we're working on is some VIC work, and also we have a separate partnership with Utah State and David's Harbotton using the Utah Energy Balance Snow Model. So this is my contact information, my co-author's contact information, and a list of the 10 or 15 people that we have involved. It takes a lot of people, a lot of cooperative people to make this work. It really does. So I absolutely want to give them credit. And I think I'm almost out of time, but we might be able to take a quick question, or these guys are the boss.
Actually, in the interest